I am Vidya Jyothi, Department of Mathematics, Assistant Professor, Department of Mathematics. I am going to teach you algebra in that group theory. Now for that algebra, in this group, algebra comes from algebra. So algebra comes from the Arabic word that is restore or complete. So this is the algebra. Now in algebra we have group theory. So first we will see what is group. So to show this group, to prove group, we have some conditions we will see. So for that we need binary operation. Binary operation. What is binary operation? We will see. Let S is a non-empty set. Let S is a non-empty set. Non-empty set. Then this S, then there exists a function f maps from S cross S to S. Then that function is said to be binary operation. So S is a non-empty set, means S should contain at least one element. So S is a non-empty set, then there exists a function f mapping from S cross S to S, then that function is said to be a binary operation. So for this we have like this. So f is a function, this is S cross S and this is S. Now if you take a comma b are the elements of S cross S, then the mapping will be in the second set, that is f of, so here you are getting a comma b are the elements of S cross S, then we are getting a circle b is the element of S. Then we say that is binary operation. So what is binary operation? Let S is a non-empty set, then f is a function from S cross S to S, then that function is said to be binary operation, right? Now next we see what is monoid or associative law. What is associative law? Let a comma b comma c are the elements of G or S. So let a, here we are taking the set is S, so take S only. So let a comma b comma c are the elements of S such that a circle b circle c can be written as a circle b circle c, then we say that is associative property. So for associative we need the three elements. For all a comma b comma c belongs to S such that a circle b circle c, whatever we are getting the left side, you should get the right side also. So that is a circle b circle c, that is associative property. Now we have next is identity law. Identity law. What is identity law? We will see. So let A belongs to S, then there exists an element E belongs to S such that A circle E equal to E circle A equal to A. Then we say that here E is said to be the identity element. So the condition is here, for all A belongs to S, then there exists a function, there exists an element E belongs to S such that A circle E equal to E circle A equal to A, then that element E is said to be identity law. Now we have the next condition, that is inverse law. What is inverse law? We will see. Let A belongs to S and from third condition you are getting E also belongs to S, then there exists an element A inverse belongs to S such that A circle A inverse equal to A inverse circle A equal to E. Then here A inverse is called the inverse element of A, then A inverse is called the inverse element of A, right? Now we have one more condition, that is commutative law. What is commutative law? Commutative law. Here for all A comma B belongs to S such that A circle B, whatever you are getting A circle B, it is same as B circle A. Then we say that there is commutative law. So this is the commutative property. Now we will go to the definition of a group. Group is nothing but, let G is a non-empty set. Here we are taking G is a non-empty set equipped with a binary operation is said to be a group if it satisfies the following properties. What are the following properties? First G1, that is associative law. Second one, identity law. And third one, inverse law. Let G is a non-empty set, then this G is said to be a group if it satisfies the three conditions, right? G is a non-empty set equipped with a binary operation. If it satisfies the three properties, then that non-empty set is said to be a group. So what is first property? We'll see. Associative law. What is associative law? We got that already for all A, B, C belongs to G such that A circle B circle C is same as A circle B circle C. This is associative law. Next is identity law. What is identity law? For all A belongs to G, then there exists E also belongs to G such that A circle E is equal to E circle A equal to A, then here E is called the identity element. Here E is called the identity element. Next is inverse law. So what for inverse law, for all A belongs to G and from third condition we are getting E also belongs to G, then there exists A inverse belongs to G such that A circle A inverse equal to A inverse circle A equal to E. Here A inverse is called the inverse of A. Here A inverse is called the inverse of A. Once again, let G is a non-empty set. Non-empty set means it contains at least one element. So G is a non-empty set equipped with a binary operation. Binary operation is nothing but the closure property. What is closure property? For all A, B belongs to G implies A circle B belongs to G. So for every non-empty let G is a non-empty set equipped with a binary operation, then it is said to be a group if it satisfies the three properties. One is associative law, then identity law, then inverse law. What is associative law? For all A, B, C belongs to G such that A circle B circle C, whatever you are getting A circle B circle C, you should get that is A circle B circle C, then we say that it satisfies the associative property. Next is identity law. For all A belongs to G, then there exists an element E belongs to G such that A circle E, whatever you are getting, if you operate A with identity element, you should get that equal to A, then here E is said to be the identity element, right? Next is inverse law. What is inverse law? From third condition, from this we got identity element is here is E. So for all A belongs to G, then E also belongs to G, then there exists A inverse belongs to G such that if we operate these two, A circle A inverse equal to A inverse circle A equal to E, then A inverse is said to be the inverse of A. Then A inverse is said to be the inverse of A. In addition to this, if we have one more condition, that is G4, that is commutative law. What is commutative law means? For all A, B belongs to G such that A circle B, whatever you are getting the result, it is equal to B circle A, then that group is said to be abelian group. Abelian group or commutative group. What is abelian group? Let G is a non-empty set equipped with a binary operation if it satisfies the associative property, identity property, inverse property and commutative property, then that set is said to be abelian group. What is the other name of abelian group? That is nothing but the commutative group. So if a non-empty set which satisfies associate with a binary operation which satisfies associative property, identity property, inverse property and commutative property, then that group is said to be abelian group, right? Next, so if a non-empty set which satisfies two properties, suppose let S is a non-empty set, so if this S is said to be semi-group, if it satisfies only two conditions, number one closure law and the other one is associative law. If a non-empty set is said to be semi-group if it satisfies only two properties, that is closure law and associative law. What is closure law? See, for all A, B belongs to S, that implies A circle B also belongs to S, then we say that is the closure law, right? What is associative law? For all A, B, C belongs to S, such that A circle B circle C equal to A circle B circle C. This is associative law. So if a non-empty set which satisfies two properties, closure law and associative law, then that non-empty set is said to be a semi-group, right? Now we have one more definition, that is monoid. Monoid is nothing but, let S is a non-empty set, which satisfies the three properties. Number one, closure law. Second one, associative law. And third one, identity law. See here, monoid is nothing but, let S is a non-empty set which satisfies the three conditions. Number one, closure law, associative law and identity law. What is closure law? For all A comma B belongs to S implies A circle B belongs to S. That is the closure law. Associative law means for all A comma B comma C belongs to S implies A circle B circle C, whatever you are getting, that should be equal to A circle B circle C. That is associative law. Next is identity law. What is identity law? For all A belongs to G, then there exists E also belongs to G, such that A circle E equal to whatever you are getting, E circle A, that should be equal to A. Then here E is said to be the identity element. So if a non-empty set which satisfies closure, associative and identity, then that non-empty set is said to be monoid. That non-empty set is said to be a monoid. Now we have one more definition, that is finite group. What is finite group? We will see. So finite group means, let G be a group which has finite number of elements, then that group is said to be finite group. So finite group is nothing but, G is a group, first it should be a group, then it has a finite number of elements, then that group is said to be finite group. For example, if you take G equal to 1 minus 1 I minus I, we know that it is a group. It is a group with respect to multiplication. Multiplication is a group, then the order of G means the number of finite group is the number of elements in that group. So how many elements are there here? That is 4. So that is order of a group. So finite group is nothing but, we can count the number of elements here. So finite group is nothing but, it is a group which we can count the number of elements in that group, then that is said to be finite group. So the example for a finite group is nothing but the fourth roots of unity. This is the example of finite group. So finite group means the number, how many elements we have in that group, then that is said to be finite group, right? Next, we have order of a group. Order of a group is nothing but, let G is a group, then the number of elements in that group is called order of a group. What is order of a group? The number of elements in that group. So how many elements are there, that is finite group, but order of a group means how many elements we have in that group, that is order of a group. For example, take the same example, that is fourth roots of unity. 1 minus I, 1 minus 1 I minus I is a finite group, right? It is a finite group. Then the order of group, so it is denoted by O of G. Order of group is nothing but, how many elements we have here? It is 4. So the number of elements in that group, is said to be the order of a group. Now similarly, you have one more example for a order of a group. G equal to 1 omega omega square. This is cube roots of unity. So G equal to 1 omega omega square is a cube roots of unity. It is a group with respect to multiplication. Now order of this group is nothing but how many elements we have? 1, 2, 3. So order of a group is nothing but 3. So order of a group is nothing but the number of elements in that group is said to be order of a group. Now we will see one problem in group. Show that the set of even integers is an abelian group under addition. So we have to show that the set of even integers is a abelian group under which operation? Addition operation. So I am taking here G equal to the set of even integers. The set of even integers. Right? Now we have to show that it is an abelian group. To prove abelian group, how many properties we have to prove? 5 properties. One is closure property, associative property, identity property, inverse property and commutative property. Right? So let the elements a comma b comma c are the elements of G. Means they are the even integers. So let us assume that a equal to 2x comma b equal to 2y and c equal to 2z are the even integers. Right? Now we will see the first property, that is closure law. What is closure law? For all a comma b belongs to G, that implies a circle B belongs to G. This is the condition. Closure property is nothing but for all a comma b belongs to G implies a circle B belongs to G. But what is the composition here he gave? It is nothing but under addition. So here for all a means what we took? It is 2x comma b equal to 2y belongs to G. That implies a means 2x, operation is plus 2y. So that equal to, we can take 2 common, so that it is x plus y belongs to G. That means it is also the resultant element is also even integer. Therefore it satisfies the closure property. Once again, for all a comma b belongs to G implies a circle B belongs to G. So here we took that a equal to 2x, it is even integer, comma b equal to 2y, it is also even integer, belongs to G, implies a circle B. A means 2x. The operation here he gave, it is plus, so 2x plus 2y. If you take 2 common, then it is x plus y. That means the resultant element is also in the form of even integer. So it satisfies the closure property. Next is associative law. What is associative law? For all a comma b comma c belongs to G, such that a circle B circle C equal to a circle B circle C. This is the property. Now here we took already a equal to 2x, comma b equal to 2y and c equal to 2z. They are the even integers belongs to G, such that a circle B, circle means here plus a plus b plus c. So this equal to, what is a? It is 2x. 2x plus 2y plus 2z. Right? I am taking only left side, that is a circle B circle C. So a circle B means a plus b plus c. So a plus b means a is 2x plus b is nothing but 2y plus c is nothing but 2z. Now in these two you take 2 as common, so that you are getting x plus y, then 2z. Now on the whole here again 2 is common, so we can write x plus y plus z. Right? Then again we can write that again it as 2 of x plus y plus z. So this can be written as 2x plus 2 of y plus z. So that means it is in the form of a plus b plus c. Or we can write here 2x plus 2y plus 2z. That means if you take LHS, that is a plus b plus c, you got that a plus b plus c. So it satisfies the associative property. Next is identity law. What is identity law? For all A belongs to G, then there we don't know what is identity element, so keep as it is first. So there exists E belongs to G such that A circle E equal to E circle A equal to A. This is the condition, right? Now here A, for all A equal to what we took? 2x. 2x belongs to G. Then we don't know what is identity, so keep as it is. Generally with respect to addition, 0 is the identity element, but we are writing as it is directly. There exists E belongs to G such that A plus E equal to E plus A equal to A. So if you take the first and last condition, then here you are getting A plus E equal to A. Now A means this is 2x. 2x plus E equal to 2x. That implies E equal to 2x minus 2x. So we can write 2 of x minus x. It is nothing but 2 into 0. So that means it is also a even integer. Therefore, E equal to 0 is the even identity element. So 0 can be written as 2 into 0, it is even integer, right? Next is inverse law. What is inverse law? For all A belongs to G, then E also belongs to G. From the third condition we are getting E also belongs to G. Then there exists A inverse. We have to find this A inverse. So A inverse belongs to G such that A circle A inverse equal to A inverse circle A equal to E. This is the condition, right? So here for all A we took that is 2x. 2x belongs to G and E also we got 0 belongs to G. Then there exists, we have to find this A inverse such that A plus A inverse means 2x plus A inverse we don't know, we are keeping as it is equal to 0. So from this we can write A inverse equal to 0 minus 2x means minus 2x. So the inverse of A is nothing but minus A, or 2x inverse of 2x is nothing but minus 2x under addition. So it satisfies the inverse property. What we have to prove? We have to prove it is an abelian group. So till here it is a group, but we have to find the abelian group. So for this we have one more property, that is commutative law. What is commutative law? For all A comma B belongs to G such that A plus B, A circle B equal to B circle E. This is the condition, right? A here is nothing but A is 2x comma B is 2y belongs to G such that A plus B means 2x plus 2y can be written as 2 of x plus y, or we can write this as 2 of y plus x, so that we can write 2y plus 2x. It is nothing but B plus A. So it is B plus A. So if you take A plus B, we got that B plus A. Therefore, G satisfies all the conditions of abelian property. Hence, G is abelian group, right? So once again, let G is in our, we took that here G is a set of even integers. We have to show that it is an abelian group. It is an abelian group. To prove abelian group, we have to prove 5 conditions: closure property, associative property, identity property, inverse property and commutative property, right? So first condition is closure law. For all A comma B belongs to G such that A circle B belongs to G. This is the closure property. So here we are taking A is nothing but the even integer, that is 2x, and B is nothing but 2y belongs to G. That implies A plus B. A circle B means here the circle is nothing but the addition. So 2x plus 2y. So 2 is common, take out, so that x plus y. 2 of x plus y means it is also, the resultant element is also even integer. So even integer means it belongs to G. So therefore it satisfies the closure property. Next is associative law. For associative we need the 3 elements. So for all A comma B comma C belongs to G such that A circle B circle C, whatever you are getting, you should get that equal to A circle B circle C, right? Now here we already took A equal to 2x, B equal to 2y, and assume that C equal to 2z, so belongs to G such that left we are taking LHS, that is A circle B circle C means A plus B plus C. So if you take LHS, then A is nothing but 2x plus B is nothing but 2y plus C is 2z. Now in these two you take 2 as common. So because 2x plus 2y, so we are taking 2 common, so that 2 of x plus y plus 2z. Now on the whole, here also you have 2 is common, so take out, then 2 of x plus y plus z. Now we can write that as 2 of x plus y plus z in one bracket. So that then expand it. So 2x plus 2 of y plus z. Again we can write this as 2x plus 2y plus 2z. So 2x is nothing but a and 2y is nothing but b and 2z is nothing but c. Therefore, if you take LHS, that is a plus b plus c, we got that is nothing but a plus b plus c. So it satisfies the associative property. Next is identity law. What is identity law? For all a belongs to G, there exists E belongs to G such that a circle E equal to E circle A equal to A. This is the identity property. Now, we assume that a equal to 2x. So, 2x belongs to G. Then, generally with respect to addition, 0 is the identity element, but here we are finding the identity element. So, there exists E belongs to G such that a circle E equal to E circle A equal to A. So, using this, for all a equal to 2x belongs to G, there exists E belongs to G such that a plus, because the operation here he gave addition. So, a plus E equal to E plus A equal to A. Now, taking first and last, so that you are getting a plus E equal to A. You can take second and last, then also you are getting E value. So, now here I am taking a plus E equal to A. Then a is nothing but 2x plus E as it is, then a, that is a is nothing but 2x. Now, E equal to, just you bring this 2x to right side so that it becomes minus 2x. So, a equal to 2x minus 2x. So, 2 is common, so take out, then x minus x. X minus x is nothing but 0. So, 2 into 0 means it is 0, that is also even integer. Next is inverse law. What is inverse law? For all a belongs to G, and from third condition we got E also belongs to G, then there exists a inverse belongs to G such that we have to prove that a circle A inverse equal to a inverse circle A equal to E. This is the identity element we should get. For that, a equal to 2x, we know already, we took a equal to 2x belongs to G. Then from third condition we got e equal to 0 is the identity element. Then we have to find out the value of a inverse belongs to G such that 2x plus a inverse equal to 0. Then a inverse equal to 0 minus 2x means minus 2x. It is also even integer, negative even integer, right? So therefore, the inverse of a is nothing but minus a. So if you take 2x is the element, the inverse of 2x is nothing but minus 2x. It satisfies the inverse property. Then we have to find the commutative law. What is commutative law? For all a comma G belongs to G such that a circle B equal to B circle A. So we know that a equal to 2x comma b equal to 2y belongs to G such that a plus b. So that is 2x plus 2y. Take 2 common so that x plus y. Again this can be written as 2 of y plus x because they are the integers. 2 plus 3 is same as 3 plus 2. So we can write x plus y as y plus x. Then expand it. So 2y plus 2x. 2y is nothing but b and 2x is nothing but a. So if you take a plus b, you got that b plus a. So G satisfies all the conditions of a abelian property. So hence G is an abelian group. Under which operation? Addition. So G is a non-empty set and it is the set of even integers. It shows all the properties of a abelian property. Then therefore G is a abelian group under addition, right?